So, ಎಲ್ಲರಿಗೂ ನಮಸ್ಕಾರಗಳು. Good evening to everyone. So, ಇವತ್ತಿನ ಉಪನ್ಯಾಸ ಕಾರ್ಯಕ್ರಮದಲ್ಲಿ ಡಾಕ್ಟರ್ ಬಿ.ಎನ್. ಚಂದ್ರಶೇಖರ್ ಅವರು ಇಂಪ್ಯಾಕ್ಟ್ ಆಫ್ ಎಲೆಕ್ಟ್ರೋಡ್ ಪೊಟೆನ್ಷಿಯಲ್ ಆನ್ ಕರೋಷನ್ ಎಂಬ ವಿಷಯದ ಮೇಲೆ ಉಪನ್ಯಾಸ ನೀಡಲಿದ್ದು ಅವರನ್ನ ಈ ಒಂದು ಉಪನ್ಯಾಸ ಕಾರ್ಯಕ್ರಮಕ್ಕೆ ಸ್ವಾಗತಿಸ್ತಾ ಇದ್ದೀನಿ. ವೆಲ್ಕಮ್ ಟು ಯು ಸರ್.
Thank you.
So, I welcome to our MD sir, Dr. A.B. Basaraj sir, and I welcome to our Academy CEO, Dr. A.M. Ramesh sir, and I welcome all the attendees and lecturers. So, I give a small introduction about the resource person, Dr. B.N. Chandrasekhar. So, Chandrasekhar sir got it MSc in 2001, 2002 from Mysore University, and has 23 years of teaching experience, and he has obtained PhD from VTU. His research interest is in heterogeneous catalysis. And Dr. Chandrasekhar sir, he has published more than 15 papers in reputed international journals, and he also has reputed a textbook of engineering chemistry, and presently working as professor in Department of Chemistry, Bangalore Institute of Technology, Bangalore. Okay, thank you, sir. Over to you.
Thank you, Sri Siddhegoda sir. First of all, I would like to thank KSTA for giving me another opportunity for sharing my knowledge among the student community. Today, dear students, today we'll be discussing about corrosion, and particularly in corrosion about impact of electrode potential on the rate of corrosion. Students, you all know, for understanding the corrosion properly, you must have the basics of electrochemistry. You all study electrochemistry, and when you study electrochemistry from the examination point of view, mainly from the entrance examination like JEE and KCET, where majority of the questions which are asked are application-oriented questions. For answering the application-oriented questions, you must have a clear, complete, deep knowledge about the concept of a particular topic. Only when you have a deep understanding of the topic, then only you can apply that particular topic and you can solve the related problems. You must have observed majority of the questions which are asked in the examination, they are all application-oriented, where you can answer the question properly only through proper understanding of the topic. Therefore, in this particular topic, we will concentrate on the deep understanding of the mechanism of corrosion, and then we'll discuss about impact of electrode potential on the rate of corrosion, and then finally we'll discuss about what type of questions can be asked in the examination regarding this corrosion as well as impact of electrode potential on the rate of corrosion. So therefore, before we discuss about the impact of electrode potential on the rate of corrosion, first of all, we shall discuss about the meaning of corrosion, why corrosion occurs and how corrosion occurs, and also we'll discuss about the mechanism of corrosion by taking electrochemical theory of corrosion. And once we understand the mechanism of corrosion, then it would be very easy for us to understand the impact of electrode potential on the rate of corrosion. See, corrosion we observe everywhere, and even though corrosion, it looks like a very simple phenomena. See, economically, corrosion, it has very high impact on economy of any country. So each and every country, it is losing about 3 to 5% of their GDP only because of the corrosion of the metallic materials. See, corrosion of the metallic materials can have very serious consequences. See, the failure of materials due to corrosion, like in nuclear reactors, high pressure boilers, the chemical plants, petroleum refineries, oil pipelines, bridges, aeroplanes, they can all have catastrophic consequences like loss of human beings and also lot of money, and therefore the corrosion, it can have a very serious consequences. For in this particular part, we'll discuss about the corrosion, why metals undergo corrosion, and under what mechanism metals undergo corrosion. First of all, see, we use several different type of materials. Among all those materials, one of the most widely used material is a metallic material. We use metallic material everywhere, mainly because there are few properties what we have in metallic materials, and those properties we cannot find in any other material. See, even today for the construction purpose, in the concrete, we go for only iron metal. We don't use any other metal. We don't use any other material. And we use iron metal mainly because of the mechanical strength of the iron. Iron exhibits very high mechanical strength. Therefore, even today, wherever we need a material of very high mechanical strength, we go for metallic materials. Another property what we observe in metals and what we don't observe in any other material is its electrical conductivity. Metals are one of the best electrical conductors what we have today, and wherever we need a material for electrical conductivity, we use only metallic materials. Everywhere for electrical connection from one point to another point, we use metallic materials. Another property what we observe in metallic materials is their optical reflectivity, shining nature. For example, you take gold metal. Gold metal we use everywhere. That is mainly because of its golden yellow color and optical reflectivity. And we don't find any other metal with a very similar optical reflectivity and shining nature as that of the gold metal. Therefore, wherever we need a material of very high optical reflectivity, shining nature, we go for metallic materials. Hence, everywhere we use metallic materials. And when we use metallic materials, one of the major drawback what we observe in case of metallic materials is these metallic materials, they show the tendency to undergo corrosion. Now the question that arises here is, why metals undergo corrosion? Metals undergo corrosion because they always show the tendency to revert back to their original nature. So you all know metals are obtained from their ores, metallic ores, and through the process of metallurgy. For example, one of the common ore of the iron is hematite ore. In the hematite ore, iron is present in the form of Fe2O3. That is, iron is present in the form of the iron compound, where the oxidation state of iron is +3, and it is not in the metallic form. You can see in the figure the hematite ore sample here. And the iron metal is obtained from hematite ore through metallurgical process, where the main reaction carried out is reduction of Fe3 plus into Fe by using appropriate reducing agent. And this reduction reaction, it requires very large amount of energy. And therefore, during metallurgical extraction of the iron metal, lot of energy is supplied to hematite ore to convert hematite ore into iron metal. Therefore, the iron metal, it is always at higher energy state when compared to the hematite ore. Therefore, when we start using iron metal for any particular application, the iron metal, when it is exposed to the environment, it shows the tendency to lose that extra energy. You all know the higher energy state is always unstable. whichever the chemical species is at higher energy state, it always shows the tendency to lose that extra energy, and it tries to lose that extra energy by undergoing a reaction in the reversible manner. And here iron metal, it undergoes reaction in the reverse manner, and it is oxidized to Fe3+ when it is exposed to the environment. And this natural tendency of iron metal to undergo oxidation to its natural form, the original form what we find in hematite ore, that is Fe3+, this we call it as corrosion of the metal. Therefore, majority of the metals, they are at higher energy state, and when they are exposed to the environment, they show the tendency to lose that extra energy, and they lose that extra energy by undergoing oxidation in the reverse direction. And that particular tendency of metal is nothing but corrosion of the metallic material. Therefore, see, when we observe corrosion of the iron metal, when it is exposed to the environment, we can very clearly observe the formation of rust over the iron. Whatever the rust is formed over the iron metal, that rust, it has lost all the metallic properties. You all know the properties of the iron metal. Iron metal, it has very high mechanical strength and it has shining nature. When the rust is formed, that rust will not be having the mechanical strength of the iron and also no other metallic properties. Therefore, the metal loses its metallic property when it undergoes oxidation. And oxidation, that is corrosion. And corrosion occurs on the surface of the metal. Corrosion is a surface phenomenon. When the metal is exposed to the environment, outer layer of the metal undergoes corrosion. Once the complete outer layer is corroded, then the another layer of the metal is corroded. And corrosion of the metal occurs layer by layer. And here, the rate of corrosion depends upon so many factors. Before we discuss in detail about the rate of corrosion, let us understand the mechanism in which corrosion occurs. The mechanism of corrosion of a metallic material, it is explained on the basis of a simple theory which is called as electrochemical theory of corrosion. The name electrochemical theory itself, it shows very clearly corrosion is because of electrochemical reaction that occurs on the surface of the metal. You all know in electrochemistry, you come across only one type of reaction, that is a redox reaction. You all know the meaning of a redox reaction. A redox reaction, it is simultaneous reduction and oxidation. It is combination of both reduction as well as oxidation. For the combination of reduction and oxidation, we use the term redox because in a redox reaction, both oxidation and reduction occur simultaneously. And both those reactions are interdependent. See, to understand the electrochemical theory of corrosion of iron metal, you must very clearly understand the nature of a redox reaction. Especially, you must understand clearly 2 points about the redox reaction. In a redox reaction, both reduction and oxidation occur simultaneously. That is the first point what you have to remember here. And the rate of both the reactions are interdependent. Rate of oxidation reaction depends upon the rate of reduction. Rate of reduction depends upon the rate of oxidation. You all know oxidation is the process of loss of electrons by a chemical species, whereas reduction is the process of gain of electrons by a chemical species. Now in a redox system, a chemical species can undergo oxidation. That is, a chemical species can lose electrons only when there is another chemical system, another chemical species present in the same system which can gain those electrons, which can undergo reduction. Therefore, one chemical species can undergo oxidation only when there is another chemical species present in the same system which can undergo reduction. When one is ready to give the electrons, then other one should be there to accept those electrons. The converse is also true. That is, a chemical species can gain electrons only when there is another chemical species which can supply the electrons. Unless there is no chemical species which can supply the electrons, the second chemical species cannot gain electrons. Therefore, what you must understand here is electrochemical reaction, that is a redox reaction. In a redox reaction, both reduction and oxidation occur simultaneously. And the second point about the electrochemical or redox reaction, what you must know here is the main driving force of a redox reaction. A chemical species undergoes redox reaction only when there is a difference in potential between oxidation and reduction reaction. The difference in potential is the driving force. The chemical species which is having lower electrode potential, it undergoes oxidation, and chemical species which is having higher electrode potential, it undergoes reduction. And electrons which are liberated in the oxidation process, they flow from oxidation reaction to the reduction reaction. Therefore, in a redox reaction, both oxidation and reduction occur simultaneously, and the driving force for the redox reaction, for initiation of the redox reaction, and for the progression of the redox reaction is the difference in potential between oxidation reaction and the reduction reaction. Reaction occurs spontaneously only when there is a difference in potential between oxidation and reduction. And again there, rate of reaction depends upon the magnitude of difference in potential between anodic reaction and the cathodic reaction. Higher the difference in potential, higher will be the rate of corrosion, rate of redox reaction. Now with this particular basic knowledge about nature of the redox reaction, we shall try to understand the mechanism of corrosion by electrochemical theory of corrosion. We shall take iron metal as an example. You can see in the figure here, we have shown a iron block, and the corrosion of the iron metal, when it is exposed to the environment, it is mainly because of the redox reaction that occurs on the surface of the iron metal. And as I said just now, for redox reaction to occur on the surface of the iron metal, there should be difference in potential across the surface of the iron metal. Only when there is difference in potential, a redox reaction is initiated. Therefore, the first condition which is required for the initiation of the corrosion of iron metal when it is exposed to the environment is the difference in potential across the iron metal. See, there are so many reasons under which a difference in potential can be generated across the iron metal. And we'll discuss one of the major reason why the difference in potential is generated later. Now, we shall assume that when the iron metal is exposed to the environment, some part of the metal is at lower potential and some part of the metal is at higher potential. And part of the metal which is at lower potential, it becomes anodic area. This anodic area is very similar to the anode what we see in the galvanic cell. So in the galvanic cell also, the basic reaction that occurs is a redox reaction. And there at anode oxidation occurs, and anode is having lower potential. Cathode reduction occurs, and cathode is having higher potential. The spontaneous reaction of the galvanic cell, it is also because of the difference in potential between two electrodes, anode and cathode. Similarly, here also corrosion of the iron metal, it is because of the difference in potential across the surface of the metal. And here, the part of the metal with lower potential, it becomes anodic area. It undergoes corrosion. It undergoes oxidation. And part of the iron metal with higher potential, it becomes cathodic area. And you all know the reaction at anode is oxidation. Therefore, in anodic area, whatever the metal is there, whatever the metal atoms are there, those metal atoms, they get oxidized. For example, when we take iron metal, Fe is oxidized to Fe2 plus by liberation of 2 electrons. This is the reaction that occurs at the surface of the anodic area. As I said earlier, corrosion is a surface phenomena. Therefore, only the iron metals which are there on the surface of the anodic area, they get oxidized, liberating Fe2 plus ions on the surface of the metal. And whatever the electrons are liberated in the oxidation process, those electrons, they move from anodic area to the cathodic area through the metal. Metal, you all know, it is a very good conductor. Therefore, electrons, they flow from anode to cathode through the metal. Now, cathodic area, it is having higher potential. Therefore, the reaction that occurs at cathodic area, it is the reduction. Now, in cathodic area, iron metal is there and iron metal is already in the reduced form. Therefore, iron metal cannot undergo further reduction. Therefore, what happens here is, whatever the chemical species which are present on the iron metal at cathodic area, those chemical species, they undergo reduction. Normally, when iron metal is exposed to the environment, oxygen and moisture which are present in the atmosphere, they are present on the surface of the metal. They get absorbed over the surface of the metal, and these O2 and H2O, they gain electrons which come from the anodic area and they get reduced to OH minus. Therefore, one of the common reaction what we observe in the cathodic area, it is the reduction of O2 and H2O into OH minus. And then in the next step, the Fe2 plus is attracted by OH minus and OH minus is attracted by Fe2 plus. And both of these ions, they move on the surface of the metal in the opposite direction and they meet in between anodic and cathodic area. Therefore, in between anodic and cathodic area, there is recombination of Fe2 plus with the OH minus, resulting in the formation of ferrous hydroxide. And this ferrous hydroxide is unstable. It further gradually reacts with O2 and H2O present in the atmosphere, and it is finally converted into the corrosion product of the iron. And corrosion product of the iron is the ferric oxide, hydrated ferric oxide, Fe2O3 NH2O. And whatever the compound we get here, this is the same compound what we find in hematite ore. Therefore, after corrosion, the corrosion product of the iron formed, it is the natural state of the iron which is available in nature in the form of hematite ore. That is, whatever the rust is formed over the iron metal, that is Fe2O3 NH2O. And we observe the rust formation in between anodic area and the cathodic area. Therefore, this is a simple explanation for mechanism of corrosion. See here, to answer any questions regarding corrosion in the examination, you must have a very clear idea about mechanism of corrosion of the metallic material. Only when you have a clear idea about mechanism of corrosion, then you can answer any type of question regarding the corrosion. Therefore, the mechanism, it is a simple redox reaction, and there are mainly three parts in the mechanism here. One is the oxidation of metal at anodic area. The second step is reduction of O2 and H2O present on the surface of the metal into OH minus. And third step is the movement of ions on the surface of the metal and combination of Fe2 plus with OH minus, and then finally formation of the corrosion product. And here the reaction that occur at anodic area, it depends upon the reaction that occurs in cathodic area, because in a redox reaction both oxidation and reduction occur simultaneously, and the rate of reaction depends upon the difference in potential between these two reactions. Higher the difference in potential, higher will be the rate of corrosion. Another point what you have to observe here is the metal is undergoing oxidation at anodic area, and this oxidation of the metal itself is corrosion. Therefore, metal is undergoing corrosion actually at anodic area, where Fe is oxidized to Fe2 plus. But the corrosion product is formed in between anodic and cathodic area. Therefore, the point where you observe the corrosion product, it is not the site where corrosion is occurring. Corrosion is occurring at anodic area, and corrosion product is formed in between anodic and cathodic area. And the cathodic area, it remains unaffected. These are the few basic things what you must understand in electrochemical theory of corrosion, and to know the proper mechanism of corrosion of a metallic material. Therefore, as per this electrochemical theory of corrosion, corrosion of the metal is mainly because of the oxidation reaction that occurs at anodic area. At anodic area, metal is oxidized to metal ion by liberating electrons. And when the electrons are liberated here, those electrons, they result in the reduction of O2 and H2O into OH minus at cathodic area. Therefore, one of the main driving force for oxidation of metal at anodic area, it is the ability of metal to undergo oxidation. Now we have so many metals in nature, and each and every metal, when it is exposed to environment, it shows the different tendency to undergo corrosion, different tendency to undergo oxidation. And from the electrochemical theory of corrosion, we understood very clearly that corrosion of the metallic material, it is mainly because of the oxidation of metal at anodic area. And oxidation of metal at anodic area, it depends upon the nature of the metal. Now, what all the metals we have in nature? Different metal show the tendency to undergo oxidation with different capacity. And the tendency of any metal to undergo oxidation, it is not the absolute capacity of the metal. It is a relative value, because a redox reaction is simultaneous reduction and oxidation. Therefore, no metal can undergo oxidation itself. A metal can undergo oxidation only when there is another chemical species present in the same system which can undergo reduction. You can imagine the working of a galvanic cell. In the galvanic cell, we use two electrodes, anode and cathode. Only when two electrodes are connected electrically and also both are connected by means of salt bridge, we observe a continuous spontaneous reaction there. And reaction progresses only when there is difference in potential between anode and cathode. Therefore, no metal can undergo oxidation itself. Metal undergoes oxidation only when it is in contact with some other chemical species which can undergo reduction. During corrosion of the iron metal, Fe is oxidized to Fe2 plus, and O2 and H2O present at the cathodic area, they get reduced to OH minus. Without cathodic reaction, anodic reaction cannot occur. Without anodic reaction, the cathodic reaction cannot occur. Similarly, whatever the metal we take, we cannot measure the absolute potential of absolute tendency of any metal to undergo oxidation or to undergo reduction. And hence in electrochemistry, we express the tendency of any metal to undergo oxidation or reduction only with respect to a standard reference. And that standard reference is the standard hydrogen electrode. And in electrochemistry, we take the potential of hydrogen electrode as 0. And we express the potential of all other electrodes with respect to this standard hydrogen electrode. And after measuring electrode potential of all the electrodes, all the metal ion system with respect to standard hydrogen electrode, we can prepare a series of electrode potential values. And this particular series, where all the metals are arranged in the increasing order of their electrode potential value, we call it as EMF series. Simply we call it as electrochemical series. In any electrochemistry textbook, you can see this electrochemical series, what we call it as EMF series. Here you can find the potential value of each and every metal ion system. At the top of the electrochemical series, here you can find lithium metal. It has the potential value of minus 3.024. And you can see the decrease in electrode potential from lithium metal till the hydrogen. The potential of hydrogen is taken as 0. And all these potentials which are mentioned here, those are the potentials of these redox systems with respect to the standard hydrogen electrode. When you connect a particular metal ion system or a redox system to the standard hydrogen electrode, few of the redox systems, they show the tendency to undergo oxidation. Similarly, when you connect the redox system to standard hydrogen electrode, there are few more systems which show the tendency to undergo reduction. And those systems, they exhibit positive electrode potential values. These are few redox systems which exhibit positive electrode potential values. You can see here at the end of the table, you can see platinum metal, gold metal, which have very high positive potential values. This series we call it as electrochemical series or EMF series. So this series is very important to understand the impact of electrode potential of metal on the rate of corrosion. Now we all know, as per electrochemical theory of corrosion of the metal is mainly because of the oxidation that occurs on the surface of the metal at anodic area. And their rate of oxidation depends upon the rate of reduction. Rate of reduction depends upon the rate of oxidation. And therefore, rate of one particular reaction, either anodic reaction or cathodic reaction, can increase the rate of corrosion of the metallic material. Therefore, higher the tendency of metal to undergo oxidation, higher is the tendency of metal to undergo corrosion. Here, metals with higher negative electrode potential, they show the tendency to undergo oxidation. And metal with lower electrode potential, they show the tendency to undergo reduction. And they show the lesser tendency to undergo oxidation and more tendency to undergo reduction. Therefore, tendency of metal to undergo oxidation and hence tendency of metal to undergo corrosion can be measured directly from their electrode potential values. At the top of the table in electrochemical series, you can find lithium metal. You all know lithium metal is highly explosive. Therefore, if you expose lithium metal to the atmosphere, lithium metal would undergo corrosion within no time. Within just fraction of second, it undergoes explosive reaction with O2 and H2O present in the atmosphere. It undergoes corrosion within few seconds with highly explosive reaction. Therefore, commonly we observe the electrical vehicle catching fire. That is mainly because of the very high reactivity of lithium metal. When it is exposed to the environment, it undergoes corrosion. It undergoes corrosion with explosive reaction within no time. Similarly, you can see different metals here. Metals with negative potential values, they show the tendency to undergo corrosion higher when compared to the metals with positive electrode potential values. Among the metals, what we commonly use, if you have observed iron metal, copper metal, gold metal, and platinum. Iron metal we see undergoing corrosion everywhere. It is because it has negative potential value, minus 0.41 volts of electrode potential. Lower the electrode potential, that is more negative is the potential, more is the tendency to undergo oxidation, and more is the tendency to undergo corrosion. Copper, which has potential of 0.34 volts, positive potential value, it always shows lesser tendency to undergo corrosion than the iron metal. And you must have observed gold and platinum metal, they never undergo any corrosion. Whatever the shining nature of the gold, we always observe that shining nature and without the surface of the gold metal undergoing any corrosion or oxidation, without losing that shining nature of the gold metal. Similarly is the platinum. That is mainly because the electrode potential of the gold is 1.5 volt and that of platinum is 1.2 volt. They have very high positive potential value. Higher the positive potential value, more is the tendency of metal to undergo reduction and lesser is the tendency of metal to undergo oxidation. Lesser the tendency of metal to undergo oxidation, lesser is the rate of corrosion of the metallic material. Therefore, gold, platinum, silver metal, which have higher positive potential values, they show very less tendency to undergo oxidation and very less tendency to undergo corrosion. Therefore, in this way, the electrode potential of a metal, it has a direct impact on rate of corrosion of a metallic material. We can guess the rate of corrosion of a metallic material just by looking into electrochemical series and looking into the electrode potential of metals. Now, there are few metals, even though they exhibit higher negative electrode potential value, they do not show the tendency to undergo corrosion. This is the exception for the electrochemical series, the trend in electrode potential what we observe in case of electrochemical series. So mainly, for example, if you take titanium metal, aluminum metal, these are the two metals which have negative potential value. Therefore, as per the electrode potential values, these two metals are expected to be undergoing oxidation very easily, undergoing corrosion very easily. But practically, titanium metal, aluminum metal, and even this chromium metal, which has the negative potential similar to the zinc metal, all these three metals, they show very less tendency to undergo corrosion. And their rate of corrosion is, it is not as per the electrode potential value. And this is mainly because of the nature of the corrosion product, which is formed over the surface of these metals. So when aluminum and titanium metal, when they are exposed to the environment, they have negative potential value. Therefore, the outer layer of the metal undergoes corrosion. Outer layer of the metal undergoes corrosion within no time. But once the outer layer is corroded, the corrosion product is formed over there on the surface of on the outer surface of the metal. And the corrosion product which is formed over here, the aluminum oxide in case of aluminum metal and titanium dioxide in case of titanium metal, these oxides are stoichiometric in composition. And these stoichiometric oxides, they cover the surface of the metal completely. And they form a non-porous, highly insoluble layer of the metal oxide over the surface of the metal. And such a metal oxide layer, it exhibits very low ionic conductivity, and also it exhibits very low electronic conductivity. And this type of oxide layer, it gives protection to the inner part of the metal, and it prevents the inner part of the metal from undergoing corrosion. And these category of the metals, we call them as passive metals. And passive metals, even though they exhibit very low electrode potential value, negative electrode potential value, when they are exposed to the environment, they do not undergo any corrosion. Only their outer layer undergoes corrosion. And the inner layer, it remains unaffected. Therefore, the impact of electrode potential on the rate of corrosion we observe only in case of the other category of the metals, what we call them as active metals. For example, lithium metal, sodium metal, iron metal, magnesium metal, zinc metal. These are the active metals. In these active metals, whatever the corrosion product is formed, that corrosion product is non-stoichiometric in nature. It is highly soluble and it is highly porous. It exhibits very high ionic and electronic conductivity. Therefore, the corrosion product cannot prevent the further corrosion of the metallic material. And hence, in these metals, the active metals, iron, magnesium, sodium, zinc metal, lithium metal, we observe the corrosion as per their electrode potential value. And here the rate of corrosion, it is directly correlated to the electrode potential value of the metal. In these metals, in the active metals, the rate of corrosion is exactly in the electrode potential value order. Among these metals, if you see magnesium metal, it has very high negative potential value. It shows the more tendency to undergo oxidation and more tendency to undergo corrosion. Lithium and sodium metals, they have even higher negative potential values, and hence they show very large potential, large tendency to undergo corrosion. Lithium undergoes corrosion within fraction of second, within no time in an explosive reaction. Sodium also, sodium metal, if you can just recall, if you want to store sodium metal is stored in kerosene. That is because kerosene is a nonpolar solvent where it will not, the sodium metal will not undergo any corrosion. Okay, therefore sodium metal is stored in kerosene only to prevent the exposure of sodium metal to the environment, because when it is exposed to the environment, it undergoes corrosion very easily. And therefore, in case of active metals, the rate of corrosion is directly related to its electrode potential value. Lower the electrode potential value, higher the tendency of metal to undergo oxidation, and higher is the tendency of metal to undergo corrosion. And higher the electrode potential value, lower the tendency to undergo oxidation, and lower the tendency of metal to undergo corrosion. Therefore, the platinum, silver, gold metal, they show very less tendency to undergo oxidation. And these metals, we call them as inert metals. And because they exhibit higher electrode potential value, lower tendency to undergo corrosion, and they exhibit higher stability. Whereas these metals, which are having lower electrode potential value, they show more tendency to undergo corrosion and more tendency to undergo oxidation and corrosion. There are few exceptions that you have to remember. That is, the passive metals like titanium, aluminum, chromium, even though they have negative potential values, they show very less tendency to undergo oxidation and corrosion because of the nature of the corrosion product, which gives protection to the surface of the metal, protection to the inner part of the metal. Therefore, uh, titanium metal, aluminum metal, the chromium metal, what we use in stainless steel, iron undergoes corrosion very easily. Stainless steel tendency of corrosion is very, very less. Aluminum metal we use for decoration purpose on the outside of the building, where we use anodized aluminum, and aluminum there it never undergoes any corrosion. That is because of the nature of the oxide layer which is formed over the surface of these passive metals. This is the relation between the electrode potential of the metal and rate of corrosion. See, for a few particular applications, we commonly use two or three different kinds of metals. When we use two different metals together, then the rate of corrosion depends directly upon the difference in potential between two metals. And this type of corrosion, actually we call it as differential metal corrosion. And rate of corrosion of a one particular metal, it is directly related to the difference in potential between two metals. Here, I've taken the example of iron metal and copper metal. When iron and copper metal are used together, for example, you can see the iron copper bolt used along with the iron nut. Here, iron has negative potential value and copper has positive potential value. And therefore, iron undergoes oxidation and iron becomes anodic area. It undergoes oxidation, it undergoes corrosion, whereas copper becomes cathodic area. It remains unaffected. And the rate of corrosion here depends upon the magnitude of difference in potential between iron and copper. You can see the difference in potential here is 0.75 volts, 0.34 minus 0.41, that is 0.75 volts. And that difference, 0.75 volts, decides the rate of corrosion of the iron metal. So same iron metal, when it is in contact with zinc metal, zinc is having more negative potential than the iron metal. Therefore, zinc undergoes corrosion here. Zinc becomes anodic area, it undergoes corrosion, whereas iron becomes cathodic area, it remains unaffected. Therefore, the electrode potential, it is a relative value. Iron metal which undergoes corrosion when it is in contact with copper metal, same iron metal, it remains unaffected when we use zinc metal along with the iron. For example, if you are using zinc bolt along with the iron nut, we can very clearly see iron is not undergoing corrosion here and zinc is undergoing corrosion. And here also the electrode potential is playing the key role in corrosion of the metallic material. And the rate of corrosion here depends upon the difference in potential between two metals. You can see the difference in potential is just about 0.35 volts here. And therefore, the rate of corrosion of zinc metal when it is in contact with iron, it is very much lesser when compared to the rate of corrosion of iron metal when it is in contact with copper. Because even though zinc is undergoing corrosion here, the difference in potential is 0.35 volts. And here iron is undergoing corrosion and difference in potential is 0.75 volts. Therefore, iron undergoes corrosion here and it undergoes corrosion at faster rate, whereas zinc undergoes corrosion here and it undergoes corrosion at slower rate than the iron metal which undergoes corrosion with respect to the copper metal here. Therefore, by the knowledge of electrode potential, the difference in electrode potential, we can very easily guess which metal undergoes corrosion, under what condition, and also we can very easily guess about the rate of corrosion of a metallic material. Therefore, the rate of corrosion, it is directly related to electrode potential. Lower the electrode potential, higher is the tendency of metal to undergo corrosion, and higher is the tendency of metal to undergo oxidation, and higher is the tendency of metal to undergo corrosion. When we use two different metals together, then the rate of corrosion, the metal which undergoes corrosion is the metal with lower potential, and the rate of corrosion depends upon the difference in potential between two metals. Thus, in this particular presentation, we have learnt about how and why corrosion occurs, and also we have tried to understand the deeply about the concept involved in the corrosion of the metallic material. We discussed about electrochemical theory of corrosion, and also we discussed about the meaning of the electrode potential and how the rate of oxidation depends upon electrode potential, how the rate of oxidation, rate of corrosion are related to the electrode potential value. And also we discussed about the effect of corrosion product on the corrosion of few of the metals, passive metals. And also we have discussed about what is the impact of electrode potential when we are using two different metals together. Therefore, with this particular knowledge, see, I told you in the beginning of the session that only when you deeply understand a particular concept, then you will be able to answer the questions effectively. Now let us take one or two simple questions here, and we shall discuss how to answer these questions based upon the concept. Application of the concept and answering the questions here. So in this particular question, I'll read out the question here. Electrode potential of iron, titanium, zinc and copper metals are minus 0.41, minus 1.75, minus 0.76 and 0.34 volts respectively. The increasing order of corrosion rate in a similar corrosion environment is. So rate of corrosion depends mainly upon the electrode potential value, and also it depends upon the nature of the environment also. And I could not discuss the nature of the environment here, but under a similar corrosion environment, here the potential values of 4 different metals are given, and you are asked to give the increasing order of the corrosion rate of these metals. See here, we have to consider two factors here, as we discussed during the presentation. Here, the first factor what you have to consider is the electrode potential of the metal. And as per electrode potential, you can see electrode potential of titanium, it is having highest negative potential value than the zinc metal, and then iron metal, and then copper metal is having 0.34 volts positive potential value. Therefore, there is no doubt that copper metal should have least tendency to undergo corrosion. Therefore, very clearly you can exclude the answer B and answer D here. These are the two answers where copper metal is having least potential value. But here, the potential of the titanium is minus 1.75 volt. Therefore, theoretically, the titanium should be having higher tendency to undergo corrosion, higher tendency to undergo oxidation. But the second concept what you have to remember here is titanium metal, it is a passive metal. The corrosion product layer which is formed over the titanium it is the protective layer and it prevents further corrosion of the titanium metal. Therefore, titanium metal, even though it has potential value of minus 1.75 volts, it exhibits least tendency to undergo corrosion. And here zinc, iron and copper metal, they are the active metals, and the corrosion rate of these three metals, it is very similar to their electrode potential order. Therefore, the correct answer in this particular case is the zinc metal is having highest tendency to undergo corrosion than the iron metal, and iron metal show more tendency to undergo corrosion than copper metal, and copper metal undergoes corrosion at faster rate than titanium metal. Even though titanium metal has negative potential value, it exhibits least tendency to undergo corrosion. Therefore, only with deep understanding of the topic and factors affecting rate of corrosion, we can answer this particular type of question. Let us take another question here. In iron, zinc, magnesium, copper metal couples, name the two metals that undergo corrosion with increasing order of their corrosion rate. Given that the electrode potential of iron, zinc, magnesium, copper metals are minus 0.41, minus 0.76, minus 2.34 and 0.34 volts respectively. Here you can very easily guess here. In the iron and zinc metal couple, the zinc metal show the tendency to undergo corrosion compared to iron because the potential of zinc is minus 0.76, potential of iron is minus 0.41. Similarly, in the magnesium copper metal couple, magnesium is having minus 2.34 volt potential and copper metal is having 0.34 volt potential. Therefore, in this couple, zinc undergoes corrosion. In this couple, magnesium undergoes corrosion. Now, the rate of corrosion. Rate of corrosion depends upon the difference in potential between two metals. In the iron and zinc metal, you can see the difference in potential is only 0.35 volts. Therefore, even though zinc undergoes corrosion here, the rate of corrosion of zinc metal is lesser here. In magnesium copper, the difference in potential is 2.68 volt. Therefore, when magnesium is in contact with copper, magnesium undergoes corrosion at very fast rate. Therefore, here magnesium and zinc metal are the two metals which undergo corrosion, and the rate of corrosion of magnesium metal is greater than zinc metal. Okay, this type of application-oriented questions, which you can answer only by understanding the concept very clearly, will be asked in the entrance examinations. Therefore, whichever the topic you study, you have to study the topic, understand the concept deeply, and then only you'll be able to answer the questions properly. With these two examples, I will complete my presentation. Thank you one and all. If there are any questions, I can take up those questions.
Thank you, sir. Thank you very much. Chandra sir.
Question. There was a question in the this one chat box actually.
Yes, yes. How does potential difference affect?
Yeah. I answered that question when the question was asked actually in the during presentation. That particular part was not covered there. At the end, I covered that particular topic also. The difference in potential affecting the rate of corrosion. I took so many examples, even in the question and answers also. The corrosion of the zinc metal with respect to iron, corrosion of magnesium with respect to copper, and all those things are mainly because of the difference in potential. The rate of corrosion also there depends upon the rate of it depends upon the difference in potential between two metals. Hope you have got the answer for that.
And one more question is there: how is the knowledge of electrode potential useful in the study of corrosion?
Knowledge of electrode potential, that's what in majority of the active metals, the rate of corrosion depends upon the electrode potential value. Directly it is related to electrode potential value. Lower the electrode potential, higher is the rate of corrosion, higher is the rate of oxidation, higher is the rate of corrosion. Only in case of passive metals, the order is not valid, and there the rate of corrosion it is not related to the electrode potential value.
ವಿದ್ಯಾರ್ಥಿಗಳೇ ನೋಡಿ, ಯಾವ್ದಾದ್ರು ನಿಮಗೆ ಈ ಒಂದು ಟಾಪಿಕ್ ಮೇಲೆ ಅದೇ ತರದ ಡೌಟ್ಸ್ ಆಗ್ಲಿ ಬೇರೆ ತರದ ಪ್ರಶ್ನೆಗಳೇನಾದ್ರು ಇದ್ರೆ ನೇರವಾಗಿ ನೀವು ಈಗ ರಿಸೋರ್ಸ್ ಪರ್ಸನ್ ಕೇಳುವಂತ ಸಮಯ. ಇಂಟ್ರಾಕ್ಟ್ ಆಗಿ ಎಲ್ಲರೂ.
If you have any questions, you can ask me here directly.
Otherwise, I sent through mail, sir.
Okay.
So anyway, we will give a very informative talk on ತುಕ್ಕಿನ ಮೇಲೆ ಎಲೆಕ್ಟ್ರೋಡ್ ಸಂಭಾವ್ಯತೆಯ ಪರಿಣಾಮ ಯಾವ ರೀತಿ ಇರುತ್ತೆ ಅಂತ ಹಲವಾರು ಎಕ್ಸಾಂಪಲ್ಗಳ ಮೂಲಕ ಮಕ್ಕಳುಗಳಿಗೆ ಬಾರಿ ಸರಳವಾಗಿ ಕನ್ನಡ ಮತ್ತು ಇಂಗ್ಲಿಷ್ ಎರಡರಲ್ಲೂ ಕೂಡ ತಿಳಿಸ್ಕೊಟ್ಟಿದ್ದಾರೆ ಸರ್. I thanks to today's resource person, Dr. B.M. Chandra Shekara, sir. Thank you, sir, behalf of KSTA and myself. Thank you, sir.
Thank you. I thank KSTA for giving me this opportunity, and also I look forward for continuous interaction with you for sharing our knowledge with the student community. Thank you.
ಮತ್ತೆ ನಮ್ಮ ಈ ಒಂದು ಕಾರ್ಯಕ್ರಮದ ಅಕಾಡೆಮಿಯ ಮುಖ್ಯ ನಿರ್ವಾಹಕರು ಮತ್ತೆ ನಿರ್ದೇಶಕರಾದಂತ ಕೆ.ವಿ. ಬಸವರಾಜರಿಗೂ ಕೂಡ ಒನ್ಸ್ ಅಗೇನ್ ಥ್ಯಾಂಕ್ ಯು ಸರ್. ಮತ್ತೆ ಈ ಒಂದು ಕಾರ್ಯಕ್ರಮವನ್ನು ಆಯೋಜಿಸಿ ನಮಗೆ ದಿನನಿತ್ಯವೂ ಕೂಡ ಕೆಲವು ಸಲಹೆ ಸೂಚನೆಗಳು ಕೊಡ್ತಾ ಬಂದಿರುವ ನಮ್ಮ ಅಕಾಡೆಮಿ ಮುಖ್ಯ ಕಾರ್ಯನಿರ್ವಹಣಾಧಿಕಾರಿಗಳಾದಂತಹ ಡಾಕ್ಟರ್ ಎ.ಎಂ. ರಮೇಶ್ ಅವರಿಗೂ ಕೂಡ ಧನ್ಯವಾದಗಳು ಸರ್. ಸೊ ಅದೇ ರೀತಿ ಈ ಒಂದು ಉಪನ್ಯಾಸ ಕಾರ್ಯಕ್ರಮಕ್ಕೆ ಇಂದು ಸೇರಿದ ಎಲ್ಲ ನನ್ನ ವಿದ್ಯಾರ್ಥಿ ಮಿತ್ರರಿಗೂ ಹಾಗೂ ಲೆಕ್ಚರರ್ಸ್ಗೂ ಕೂಡ ಮತ್ತೆ ಟೀಚರ್ಸ್ಗೂ ಕೂಡ ಧನ್ಯವಾದಗಳು ತಿಳಿಸುತ್ತಾ ಈ ಒಂದು ಕಾರ್ಯಕ್ರಮವನ್ನು ಮುಗಿಸೋಣ ಅಂತ ಹೇಳ್ತಾ, ಮತ್ತೆ ನಾಳಿನ ಒಂದು ಉಪನ್ಯಾಸ ಕಾರ್ಯಕ್ರಮದಲ್ಲಿ ರಿಚರ್ಡ್ ಗೋನ್ಸಾಲ್ಸ್ ಅಂತೇಳಿ ನಮ್ಮ ರಿಸೋರ್ಸ್ ಪರ್ಸನ್ ಅವರು ಸೊಲ್ಯೂಷನ್ಸ್ ಎಂಬ ವಿಷಯದ ಮೇಲೆ ಉಪನ್ಯಾಸ ನೀಡಲಿದ್ದು, ಇಂದಿನ ರೀತಿ ಎಲ್ಲಾ ವಿದ್ಯಾರ್ಥಿಗಳು ನೋಡಿ 320 ಜನ ಆಯ್ಕೆ ಆಗಿರೋದು ಚಂದ್ರ ಅವರ ಮಕ್ಕಳು ಕೆಲವೇ ನೋಡಿ 100 ಜನ ಮತ್ತೆ ಯೂಟ್ಯೂಬ್ ಅಲ್ಲಿ 1 ಜನ ಜಾಯ್ನ್ ಆಗಿದ್ದಾರೆ. ಇವ್ರಿಗೆ ಮಂತ್ಲಿ ಸ್ಕಾಲರ್ಶಿಪ್ ಕೂಡ ಇದೆ. ಇವ್ರು ಇದೇ ರೀತಿ ಅಟೆಂಡ್ ಆಗ್ಲಿಲ್ಲ ಅಂದ್ರೆ ನಾವು ಮಂತ್ಲಿ ಸ್ಕಾಲರ್ಶಿಪ್ ಕೂಡ ಇವ್ರಿಗೆ ಅಂದಿಸುವಂತ ಸಲಹೆನ ಕೊಡ್ತಾ ಇದ್ದಾರೆ ನಮ್ಮ ಸಿಇಒ ಅವರು. ಸೊ ಹಾಗಾಗ್ದಂಗೆ ನಾನು ಹೇಳ್ತಾ ಇದ್ದೀನಿ, ಮತ್ತೆ ನಮ್ಮ ರಿಸೋರ್ಸ್ ಪರ್ಸನ್ಸ್ ಒಬ್ಬರಡೆ ಹೇಳ್ತಾ ಇದ್ದಾರೆ ಎಲ್ಲ ಜಾಯ್ನ್ ಆಗಿ ಹೆಚ್ಚಿನ ಸಂಖ್ಯೆ ಅಂತ. ಎನಿವೆ, ಥ್ಯಾಂಕ್ ಯು ಸರ್, ಥ್ಯಾಂಕ್ ಯು ವೆರಿ ಮಚ್.
Thank you.
Okay, thank you, Ananda.